So in the previous video, we showed that the cardinality of the naturals was equal to the cardinality of the integers. And in this video, we're going to be comparing the cardinality of the naturals to the cardinality of the rationals. So recall that the rationals, I still have the definition of the integers here so that because it's used in the definition of the rationals are any numbers that can be written as a divided by b, where a and b are both integers. This symbol means in or an element of, so a and b are in the integers, or a and b are elements of the integers, and b does not equal 0. Dividing by 0 causes lots of problems. So that's what the rationals are. 1 over 2, 17 over 15, 200 over 300. So in this case, it can be simplified further to 2 over 3. So these are the same rational number, even though they're written differently. But yeah, that's all. So quickly, let's look at a number line to kind of get some intuition about the two sets that we're comparing. So we can say zeros over here, 1, 2, minus 1, minus 2. And so let's first underline the natural numbers in this line. We have 1 and 2 here, and it'll continue this way, evenly spaced forever. But now let's think a bit about the rationals. We have rationals between 0 and 1, 1/2 is an example, 2/3 is an example, 3/4 is an example. Then there's rationals over here, 3 over 2. There are negative rationals, minus 1 over 2, minus 3 over 2. And one thing we can show is that the rationals are dense in the real numbers, meaning that for any real number you choose, real numbers are any number here. Anywhere you pick, it can be written as a decimal expansion, either a terminating one, which makes it rational, or even repeating decimals are rational, but there are also irrational numbers like pi, e, and the square root of 2, which can only be written as an infinite non-repeating decimal. So the reals are any of those, but for any real number, you can get as close as you want using rationals. So one simple way to show this is how you can get infinite rationals that are close to 1, but not quite 1. So we have 1/2, 2/3, 3/4. You can get closer by doing 4/5, 5/6, and so on. And what I'm doing here is numbers of the form x divided by x plus 1, where x is a natural number. So if you choose a very large x, suppose 1,000, then the denominator is still bigger. 1,000 plus 1 is 1,001. So 1,000 over 1,001 is slightly less than 1, but it's very, very close. But you can also continue to go higher. If you pick an even larger value for x, then you'll get even closer to 1. And you can keep making x larger for as long as you want, and so you can get arbitrarily close to 1 without actually getting there. And so again, this is said that the rationals are dense in the real numbers, because this isn't just true for 1, it's true for any real number. You can get as close as you want to it without even necessarily that number being a rational number itself. In this case, 1 is a rational number, but it also works for pi, for example. You can get rational numbers as close to pi as you would like. So for this reason, this density of the rationals makes it seem hard to believe that the naturals and the rationals can have the same cardinality, because there seem to be so many more rationals. There are infinite rationals between 0 and 1, I've just shown you. So for that reason, like that, our intuition is that there should be more rationals than naturals, but our intuition is already kind of going out the window with infinities, based on the previous video where we showed that there are the same cardinality for the integers and for the naturals. So we'll see if our intuition matches in this case. So suppose we are trying to see if there exists a bijective function from the naturals to the irrationals, a function which takes every element of the naturals to a different element of the rationals, and which covers, and this mapping eventually covers all of the rationals. So we can try and think of this as like a first element of the rationals, which is mapped to by 1, a second element, which is mapped to by 2, and then a third, and so on. And if we can kind of count all of the rationals, if we can eventually get to all of the rationals, then there's a bijective function, because you can just have that way of counting the rationals systematically as your function. So let's see if we can kind of come up with a systematic way to arrange the rationals so that we will get to all of them if we approach them in the correct way. So think a little bit about how you might try to systematically arrange the rational numbers. Pause the video if you want to try that on your own for a little bit. But continuing, we can start by maybe considering all of the rationals with a denominator of 1. And so we can start with 0, and then we want to cover every possible numerator that goes along with this denominator, and it just has to be an integer. So a can be any integer. So we want to cover rationals with any integer in the top and 1 in the denominator. So now we have to find a way to systematically arrange all of the integers. But we've already done that in the previous video. How do we do it? We started 0, then 1, then -1, then 2, then -2, and so on. So this is a way to arrange all of the rationals that have a denominator of 1. But that's not everything. We can next look at rationals that have a denominator of 2. So we can do the same thing. Then 1 over 2, minus 1 over 2. And now we run into this idea of non-simplified fractions. Since 2 over 2 and 1 over 1 are the same, we can skip over this and not list it. And the same is true of -2 divided by 2. That's the same as -1 divided by 1. So then we can just continue on to the next numbers that are not already listed. And we can continue like that. Yeah. And then we can move on to 3 in the denominator and do the same thing. Again, skipping over anything that's already been listed. Actually, you're unlikely to find, every third one will be an integer. So yeah, you'll still have to skip some in this row as well. So for example, 3 divided by 3 and -3 divided by 3. But yeah, that's the basic idea. You have a way to list everything that's has a denominator of 3 as well. And you can really continue this for growing denominators, 4, 5, 6. I haven't listed any negative denominators, and you don't need to in this case, because -1 over 1 is the same as 1 divided by -1, and -1 over 2 is the same as 1 divided by -2. So by accounting for all of the negative integers in the numerators, we're already accounting for every possible rational that would have a negative denominator. Yeah, and also -1 over -1 is the same as 1 over 1. So cases where both the numerator and denominator are negative are also already accounted for by cases where the numerator and denominator are both positive. So now we've kind of arranged this table where there's a top left corner, and it extends infinitely out to the right and infinitely downwards, where the numerators get larger or more negative as you move to the right, and the denominators get larger as you move down. So now we want to see, is there a way, the goal of this systematic ordering was to find a way to think of a first rational, a second rational, and continue to count upwards while accounting for every possible rational number. So now I think it makes sense to start with 1 in this top left corner, but then how do you want to continue counting so that you get a second and a third, and eventually by counting 1 by 1, you eventually hit every rational number in this infinite table. And you can think about, again, is this possible, and how would you do it? Pause the video if you want to try and think about that, and I will now go ahead and tell you the solution. So it is in fact possible to come up with this bijective function to count all of the rationals in a systematic way. So one way you can do this is by kind of zigzagging across this table. So that would mean, so by the way, when I wrote the 1 here, that meant you can think of the function having f of 1 equals 0 over 1, or just 0, and that's kind of the mapping. I'm just writing the natural in blue next to the rational. So zigzagging by having f of 1 equal this, f of 2 equals 1 over 1, f of 3 equals, oh actually 0 over 2, I didn't erase that. In all of the other zeros are also the same, so we can also ignore that one and kind of cross those out because they're also redundant. But so then this would be moved over actually. So let me, it does look visually more clear, this proof, when everything is aligned properly. So I will erase this and move things over a little bit. So instead of starting with zeros in the numerators, we'll start with 1 because that's the first case where you don't have a redundancy every time. So recall we skipped 2n minus 2 here, and this will be 1 over 3. Yeah. So now this zigzagging take you here, then you can come here, then you go down further and zigzag back up and down. And so you continue to move in this manner, going across in diagonals back and forth. And you can see that since this table only extends right and downwards, and the zigzagging is covering right and downwards systematically, you will eventually get to every rational number. And then the natural number that you've written next to it will be the natural which maps to it. And if you do this infinitely, you have a bijective function where f of 1 equals 0, f of 2 equals 1, f of 3 equals 1/2, and you just continue, and you have a natural number mapping to every rational number, because every rational number is somewhere on this table, because we have accounted for every possible numerator and denominator that are integers. And so this shows that the cardinality of the naturals does equal the cardinality of the rationals. I would have a hard time writing this function explicitly. It's much easier to see with this table, and it gets confusing having to skip the fractions which aren't in simplest form. So I'm not going to make too much effort to write the function in a very general form, but you can see that for any irrational you could give me, if I just continue down this table long enough, I would have a natural number that does equal that. And that shows exactly what we wanted to, which is that there's a bijective function from the naturals to the rationals. And this is not the only way. This zigzagging isn't the only way to systematically cover every element in the rationals. So we can also do a different order. So I'll show you one other way. So it still probably makes sense to start with the first one in the top left. But after that, you can kind of think of it as covering a corner of a square. So 2, 3, and 4 would be here. You covered that corner. Then you move on to the next corner that looks like this. Oh, I misnumbered. Already did 4. And continue onwards like that. So essentially, after each iteration, you will have covered a corner of a slightly larger square. And eventually this also will have every element in the rationals, because you just continue to cover more and more to the right and downwards. So eventually you get to everything. And again, what this tells us is that the cardinality of the naturals is equal to the cardinality of the rationals. And this is even more intuitive than the fact that the naturals and the integers have the same cardinality, because because of the fact that the rationals are dense in the reals. And yet these ways of thinking about a bijective function show that it is in fact true. Thank you for watching.